All right. So today we're going to be talking about DC machines. Let me go hit the light real quick. So as I said a moment ago, today we're going to be talking about DC machines, and I've decided to utilize a couple of graphics here that will make our life a little bit easier to understand what's going on. So this is kind of a cutaway view of a relatively simple DC machine. So we have the frame, also commonly called the yoke, our stator, our armature, which is our rotor, much like we had in the synchronous machines. We've got our shaft and bearings and all of that kind of good stuff just for helping things rotate smoothly. And then we have that thing called a commutator and a brush assembly on the right-hand side there. And the commutator and the brush are the biggest difference between a synchronous machine and a DC machine. So we're going to spend quite a bit of time talking about the role of those things today. Now, this diagram, I think, is pretty straightforward. However, I have another diagram down here from our textbook that gives a better illustration of the internal workings of the device. And as you can see, this is a rather busy looking diagram that's going to take us a little bit of time to kind of unpack everything. So this picture is of a simple two-pole machine, meaning it only gets way more complicated if we have more poles going on, okay? So let's start with what's going on with the stator. Just a second. So the main parts of the stator are the stator yoke, which is just the outside of the housing. And then we have our main pole core. And as you notice here, there's a label for N and there's a label for S. This is for the north and south pole of effectively just a large electromagnet, right? So in a DC machine, it should not be any stretch of the imagination to think that our stator is going to be excited with a DC signal. And so that's going to give us effectively a DC magnetic field in our system. So we're going to have a magnetic field that is oriented from the North Pole to the South Pole, running through the armature, and then it is going to see two parallel paths wrapping back around, back to the North Pole over on the top side and on the bottom side. So our pole cores, so that's this bit. Let me put a little mark here in green or something. So these bits right here, they have two windings, okay? They have what's called a series winding and a shunt winding. And the stator can be excited by either of these field windings. So the shunt field winding has numerous turns of very thin wires that are connected in parallel with the armature circuit. And the series field windings has a small number of turns using very thick wires that's connected in series with the armature circuit. So this is our way of saying effectively if we want high current or low current applications, we use a different set of windings. And as we talk more about the various different connections that we can have, we'll see that in some cases, the series windings and the shunt windings are both utilized to give us interesting things like self-excited configurations and all that kind of good stuff. So we'll talk about that more on Tuesday. Okay. The The series and the shunt windings lie on the direct axis or D axis of the machine, labeled right here. The field poles usually also contain compensation windings, which are shown. Let me circle them in. Let's do this light blue here. So these are our compensation windings. And the compensation windings are wound parallel to the rotor surface, and they reduce field distortion and reduce brush arcing experienced in the machine, okay? So effectively, there are some carbon brushes that I'll talk about in a minute, and they're constantly rubbing against the armature as it spins. That's going to cause mechanical damage over time. And there's also electrical damage over time because as they get dragged, they spark and arc and try to burn little divots and stuff like that into the armature. And so these compensating windings are just a way to try to minimize that arcing so that there's less damage sustained by the machine during its normal operation. The armature winding, which is, let me do it in, I don't know, maybe dark blue. All of these bits right here. We'll have a fun talk about lap winding and wave winding in a little bit. But the armature winding is where induced voltages and currents occur, which generate the torque for rotor movement. The commutator is located on the armature and is made of conducting segments that are formed into a cylinder and separated by an insulating material. So we've got effectively a whole bunch of conductors set in series. We slice it up and we insulate them, and we'll talk about the role of the commutator here in a little bit. Current is conducted to the armature coils by brushes that ride on the commutator segments. The commutation of the armature current can cause arcing at the trailing edges of the brushes. This is avoided by including commutator poles, which are these guys 90 degrees out of phase with the main poles. They are considered to be in quadrature. All that really means is 90 degrees out of phase. And so that's why we have a Q axis up there at the top that is exactly 90 degrees off from our direct axis. So now that we kind of have an idea of what the various different parts are and what they're for, let's talk more in depth about what the commutator actually does. So I'm going to attempt to draw some crappy pictures here. So we're going to start by looking at a motor. And what would happen without the commutator. And this is going to be a very, very simplistic drawing, okay? So the first thing that I'm going to put here is the cylinder. And on this cylinder are slip rings, okay? This is what's used on the armature of a synchronous machine, okay? So let me put this in gray. And so what the slip rings are going to allow is effectively rotation to occur while still maintaining electrical contact to an external system. Okay. So I'm going to connect to this slip ring right here. So I'm putting a blue dot here and then a blue dot here. And I'm going to just put a single loop of wire. Okay, so instead of worrying about multiple turns and this, that, and the other, let's start as easy as we possibly can with just a single loop for our armature winding. I'm going to call this segment AB and this segment CD, like so. And then I'm going to have another portion of the electrical circuit over here. So this black box is going to represent a brush, B1. And this black box down here is going to represent a brush, B2. And then connected to my brushes are wires that will form part of the circuit. Since this is a DC machine, I'm going to excite everything with a simple DC voltage source, which I'm representing with a battery here. So I'm going to call this VA for my armature voltage. Okay. So this is my armature system in a simplified form. I'm going to make my field system or my stator even more simplified by just replacing it with a permanent magnet. So imagine that I have some sort of magnet. Here's the North Pole. Over here is the South Pole, right? So that I have a magnetic field B that's oriented from left to right across the page here. So let's look at the direction of current flow in this system, right? So since this is a DC circuit and I only have a single voltage source, it shouldn't be any huge stretch of the imagination to realize that my current is going to be leaving the positive polarity terminal of my battery, flowing around its path, and then entering back into the negative terminal of my battery, right? So I should have some armature current IA like so. Then it's going to travel, hit the brush, flow into this slip ring, flow from A to B, from B to C, from C to D, back through, hit brush 2, and flow down like so on its return path. So I want us to look at the forces that are acting on our loop so that we can see what's going on here, right? So over here to the right, I'm going to draw the important parts of our system. So here's the North Pole of our magnet. Here's the South Pole of our magnet. Here in the middle in red, I'm going to put my magnetic field vector B. Okay. Now, I'm going to have two conductors. So this guy right here is for conductor AB. And this guy right here is for conductor CD. So those are just the two parts of the path the magnetic field are going to act on, right? From our diagram, I can say that the current flowing in segment AB is directed into the board. So that's going to look like an X, and the current CD is coming back at us out of the board. So I'm going to put a dot there. Now, we've talked about the Lorentz force law a little bit when we were dealing with, I believe it was synchronous motors. Just to refresh your memory, the Lorentz force law, F is equal to I crossed into B. So what should the direction of the force that's acting on conductor AB be? Okay. So my current is flowing into the board. My B field is flowing from left to right. And so I've contorted my arm in such a way that my thumb is in the direction of our force, which should be down. Okay. So we'll have some force flowing down or directed down, acting on conductor AB. Since the current CD or the segment CD, the current is in the opposite direction, the force should also be in the opposite direction. So we'll have a force up. And because we have these two forces acting in opposite directions, we're going to wind up having some torque, T, that's going to try to make that loop spin in a counterclockwise direction. Everybody okay with this? Okay. Let's look at what happens with this exact same system, except that now we've allowed our loop to rotate exactly 180 degrees. Right? So to make this a little quicker, let's copy all this stuff and let's paste it down here. Now I need to edit some things. Oops, erased a little more than I wanted to, but that'll be okay. All that's still the same. Don't need that again. So let me fix my slip rings and all of that kind of good stuff. Still there. B1's on the left, B2 is on the right. Now what we should see is that brush 2 is connected here. So here's D, C, B, and A. Like so. So all I've done here is just allow my loop to spin 180 degrees. Okay. If we look at our direction of current flow, right, now we should see that current is flowing into the page on segment AB and out of the page on segment CD. We all okay with that? So if I put my conductors back here, so this guy right here is going to be CD. This guy over here is going to be AB. So AB is, oh goodness gracious. Into the page, CD is out of the page, and we already know how our forces should work, right? So we should have a force directed up acting on conductor CD, and we should have a force acting down on conductor AB. And so our torque has effectively changed directions. It's now going to want to make our rotor spin clockwise. So 180 degrees of mechanical movement winds up causing a complete reversal in the direction of our torque. So instead of having a continuous rotation, we're gonna rotate and then go back and rotate and go back and rotate and go back over and over and over again. That does not make a good motor by any stretch of the imagination, because we need continuous movement in a single direction, which means we effectively need a unidirectional torque, okay? So now, let's revisit this with a commutator. How did I do this? So here, let's include commutator. There we go. So similar thing. I'm going to have my simple DC circuit down here. Here's my armature voltage VA. My brush B1. My brush B2. I'm going to do my commutator here in red. So let's call this C1 and let's call this C2. So effectively, all I've really done is I've just split those slip ring assemblies into two distinct pieces that are separated by a gap here. So a form of electrical isolation, so that commutator 1 is going to be in contact with brush 1 for half of the cycle, and then commutator 1 is going to be in contact with brush 2 for the other half of the cycle, right? Now I'm going to draw my little loop of wire. Once again, we have segments A, B, C, and D. Here's my north pole of my stator field. Here's the south pole of my stator field. And let's look at our current directions, right? So we're going to have our armature current IA flowing up. That's going to flow into the page for line segment AB, back out of the page for line segment CD, before flowing down through brush 2 and returning to the negative polarity terminal. So for all intents and purposes, our force diagram is effectively going to be the exact same thing that we saw for the first half cycle of our slip ring connected device. B field here in the middle. So here's segment AB, segment CD. Current is flowing in through AB, out through CD. So we should have a force down here and a force up here, resulting in a counterclockwise. If we allow our loop to rotate 180 degrees, what we're going to wind up seeing is something that looks like this. Here's brush 1, brush 2, those guys are stationary. Now commutator segment 2 is going to be on the left, and commutator segment 1 is going to be on the right. So here's D, C, B, and A, like so. And now, oh, let me draw my magnets. Apologies. North and south. So if we look at our current, it's going to flow up into the page for segment CD, out of the page for segment AB, and then down like so. And drawing my little force diagram to figure out what's going on with the torque is going to look something like this. So here's CD, here's AB. So CD, the current is flowing out. AB, the current is flowing in. And so we have a downward directed force on CD, an upward directed force on AB. And our torque is still in a counterclockwise direction. So now we should see that the motor only wants to spin in a single direction. If we were to reverse the polarity of our applied armature voltage, what would happen? Yeah, our motor would just spin in the opposite direction. This is something that you guys probably should have realized maybe as early as ENGR or ENGT 120. You guys use little DC motors in that class, probably for a pump or something like that. If you applied the wrong polarity to the voltage, your impeller was spinning the wrong direction, and it was really inefficient at moving water around. All right, so what is the commutator doing here? Yeah, so effectively, if we look from the perspective of, let's just say, conductor AB for this portion, you've effectively got it. What it's doing is it's allowing the current to change directions in that particular portion of the loop. Or another way to think about it is it's allowing the voltage of the opposite polarity to be applied to the terminals of the loop. So some people like to say that the commutator converts the DC voltage or DC current into an AC voltage or current. I don't really like that personally, because to me, when I hear AC voltage or AC current, I'm thinking of sinusoidal voltages and currents. Instead, it's changing the direction of the current or changing the polarity of the voltage. It's still going back and forth between two things, so it's not technically DC anymore, but I don't really like calling it AC because it's not sinusoidally varying. Instead, we're kind of getting like a square wave. So half the time it's a constant value positive, and the other half of the time it's a constant value negative, okay? So without a commutator, the motor literally would not work, okay? So now let's look at the role of the commutator for a generator. Scroll too far. So once again, I'm going to try to draw something very, very simplified. Here. So generator, and let's, now that we know what the commutator is doing, at least for a motor, we can probably figure out what it's doing for a generator. So similar thing here. This is effectively going to be my north field pole. This thing down here is my south field pole. And once again, we're going to look at a single loop of wire. And should have used consistent colors as before. Give me just a second. I don't want to be confusing. So these are our parts of the magnets, which were in this light blue color like before. Our single loop here going to be something like this. And then my commutators are in red. My brushes are in black. And then this is my voltage seen at the terminals of my generator. I'm sorry, what? Of T. Yep. So using subscript T for my terminal voltages. And then just for the sake of argument, over here on the right-hand side, I'm going to connect some resistive load just so that I have current flowing in my network. So we're looking at this in terms of a generator, which means we have something that is mechanically causing our loop there in the middle to rotate with some angular velocity or angular frequency omega. Okay. All right, so what do we know about generators? Effectively, it should be almost the complete opposite of what we just did with the motor, right? So we are effectively going to be inducing currents and voltages due to a change in the flux seen by our loop, right? So as this loop spins with angular velocity omega, if we were using slip rings, so here's time, and here's Vt as a function of time. Well, let me do it in this purple color. Let's see. So right now the flux is effectively 0, but the change of flux is going to be as large as it could possibly be. So this is going to look like the positive peak of our voltage. As the wire loop spins, so if it spins 90 degrees, our terminal voltage would hit 0. As it spins another 90 degrees, we would hit negative the maximum value. another 90 degrees back to 0, and so on and so forth. So let me put here without commutator. We've already seen this because this is exactly how synchronous generator works. If we include the commutator, though, what's going to happen? Well, for our first quarter cycle, as it were, things are going to be exactly the same. Now, because of the commutator, the polarity of our induced voltage is going to change, which means instead of having a negative half cycle, we're going to have a positive half cycle. And that's going to continue to happen over and over and over again, like so. So in this perspective, we can say that the commutator is providing rectification. Have you guys had any classes dealing with electronics or anything like that? Kinda. You guys ever heard of a full wave rectifier? Sure. So in a full wave rectifier, and that's typically done in an electronic circuit with a combination of diodes and all of that kind of stuff, effectively what it does is it gets rid of all of the negative half cycles. So a half wave rectifier literally just throws those negative half cycles away because the diode only allows current to pass in one direction. In a full wave rectifier, it actually flips the polarity and we get something like this. So we get the exact same thing, effectively full wave rectification without the use of any semiconductor-based electronics in our system. So that's pretty interesting. What would happen if we had more than one coil and we split our commutator up into more than 2 segments? So if we had more than one coil rotating in this thing, each with its own associated positive and negative polarity for the commutator, effectively we'd see something like this. So I'm going to have another loop here that's a little bit out of phase. And let me put another one here. And maybe another one right here. And effectively, the more loops we wind up having, the closer and closer we get to a DC voltage. So the output voltage is just going to be this ripple thing on top that I can't draw for crap. But the more coils that we put in and the more segments that we subdivide our commutator into, our output voltage across our terminals is going to look more and more and more like a DC voltage. So in the sense of a generator, our commutator is providing rectification and to some extent filtering, right? By smoothing things out. So commutator is absolutely integral to how a DC machine works as both a generator and as a motor. All right, so now let's talk about some quantities here. Let's start, and this might be the only one that we get to today, with the armature voltage. So the armature voltage is the induced internal voltage in a DC machine. Mathematically, our armature voltage is given by the relationship EA is equal to Z, we'll talk about that in a moment, E divided by 2 pi A times phi D times omega M. So let me explain what these constituent parts of this equation are. So Z is the total number of conductors in the armature winding. So let me do this here in blue. Z is always going to be equal to 2, because as we saw previously, let me go back up here. Even though we have, in this case, just a single loop of wire, our magnetic field is acting on 2 segments of conductors in this loop. So that's where the 2 is coming from. Then it'll be the number of turns in our coil times the number of coils, because we know that we might need several coils in order to smooth things out, okay? So that's what Z is all of the time. P is the number of poles that we have. And this should be in the stator. So it's always going to be a multiple of 2. Depends on how many windings effectively we have in the stator, right? Here's one that is a little bit weird. A is the number of parallel paths in the armature winding. And this number depends on the mechanical construction of the device. So there are 2 different types of windings that are used for the armature of a DC machine. We have what's called a lap winding, and then we have what's called a wave winding, okay? So this is kind of a subtopic inside this definition that we have to sort out now. So let's start by looking at a lap winding. So in a lap winding, we're going to have something like this. So imagine I took my commutator and instead of having it in a cylindrical form, I effectively unrolled it. So I were to slice my cylinder and then unroll it out, where this is commutator segment 1, commutator segment 2, commutator segment 3, so on and so forth. And this would repeat on both sides so that it's connected together, okay? So in a lap winding, if my coil starts on commutator segment 1, it's going to wind up ending on commutator segment 2. So I might have something like this. So we have starts on one, it ends on the subsequent segment. So this is coil 1, and then coil 2 would do something like this. So it would start on 2 and end on 3. And so on and so forth. So it's called a lap winding because the windings overlap. Okay. Now, in a lap wound system, the number of parallel paths is always equal to the number of poles and the number of brushes needed for smooth motor operation is also equal to the number of poles. So lap windings are typically used when we have an application that requires low voltage and high current. Typically speaking, they are more expensive than their wave wound counterparts because it requires more wire to form the winding and can require more brushes for a multi-pole system. So two things contribute to their expense, right? So more copper used means it's more expensive. More carbon brushes used also means it's more expensive. So the only time it ever makes sense to use a lap wound machine is specifically when you want low voltage and high amounts of currents because of effectively this way that everything is connected. In contrast, there's also what's called a wave wound DC machine. Okay. So wave winding looks something like this. So let's take that same commutator, roll it out. Like so. Here's segment 1. And I'm going to start segment 1 here, or excuse me, coil 1 on segment 1 of the commutator. And instead of making my coil end at the next successive commutator segment, I'm going to make it end significantly further down the line. So if I drew this right, this should be section 6. Okay. 2, 3, 4, yep, 5, 6. And then we can do the exact same thing for coil 2. So it's going to start where coil 1 ended, and then we're going to spread it out like so. And this commutator segment here should be number 11. And on like that. So it's called a wave winding because it looks like a wave. So, I don't know, bored engineers. Okay. So this wave winding has some interesting characteristics that are distinctly different. Okay. There will always only be 2 parallel paths. So let me write that down. And the number of brushes is always 2. These are typically used in the exact opposite situations as lap winding. So used in high voltage low current applications. Requires significantly less wire to get the same job done, so typically cheaper. And since it's always 2 brushes, there's never any additional expense there. Okay. So for a wave wound machine, that coefficient A is literally always 2. For a lap wound machine, that coefficient A is equal to the number of poles. So that means that we're going to get literally different induced voltages depending on whether our DC machine is lap wound or wave wound. Okay. All right. So let's see. We've got Z taken care of. We've got P taken care of. We've got A taken care of. So now let's talk about phi D and omega M. So back to our definitions. Phi D is the direct axis air gap flux per pole. So that's literally just the amount of magnetic flux passing through the stator windings. And lastly, omega M is the exact same thing it's been since we started talking about motors, mechanical speed at which the shaft is rotating. So often the term ZP divided by 2 pi A is expressed as Ka, where Ka is just known as the armature constant. And so this effectively just lumps together all of the different ways that the fabrication of the machine influences the induced voltage, right? Because this takes into account total number of conductors, total number of poles, also part of the fabrication, whether it's lap wound or wave wound, it's all boiled into this one simple parameter so that our induced voltage, EA, becomes Ka phi D times omega M. All right, so the last thing that I want to do for today is work a very quick example. Let's say that the armature of a 4-pole DC machine is operating at 1,000 RPM. The armature winding consists of 33 coils. Each coil having 5 turns. The magnetic flux per pole is phi D is equal to 50 milliwebers. And I want us to determine EA for a lap wound machine and a wave wound machine. So let's start by figuring out Ka for a lap wound machine, right? So Ka will be ZP over 2 pi A. So what should Z be? 2 times the number of turns in each coil. So 5 times the number of coils, 33. We have 4 poles. What should A be? So it'll be 4. I thought somebody said 8. Oh, P. Okay, sorry. Yeah, so same thing as P. Absolutely right. So also 4. So these guys wind up just canceling each other out. And this comes out to be 52.521. Yes. Our induced voltage for our lap wound system is then Ka times phi d times omega m. Might find out just a second that this does need units, but we'll sort that out in a second. So we're going to have that 52.521. I'm going to leave enough space here to put units in if I need them. Phi d is 50 milliwebers, right? So that's 50 times 10 to the minus 3 Webers, where a Weber is a volt second. And then we have our speed, 1000 RPM. So that's rev per min times 2 pi over 60. So that 2 pi over 60 is converting it into radians per second, right? So I'm just going to scratch that and put rad per second. Notice here now, this second and this per second cancel. Radians is a dimensionless quantity. And so the output of this is just going to be a number in volts. So unitless is actually correct for that armature coefficient. So let me throw this in my calculator really quickly. Two pi over 60. 275 volts. For our wave wound machine, you had a question, Lance? So ZP over 2 pi A. So Z is going to be the same. 2 times 5 times 33. Still have 4 poles. What's A for a wave wound machine? Always 2. Which means effectively our armature coefficient is just going to be twice as large. So 105.042. And because our armature coefficient is twice as large, our induced voltage should also be twice as large. So this should look like 550 volts. All right. So I think this is a good stopping point for today because we've spent a lot of focus on how these things work. So in our next class meeting, we'll talk about how we connect them and all of that kind of good stuff, look at equivalent circuits, and then do our analysis. To me, the how they work part of things is actually way more difficult to understand than anything else because there's so many complicated type things going on. One of the great things about DC machines is while they are a pain to design, etc., they are the easiest machine to control because it's just applying DC voltage. Okay, you had a question? Don't know. I can look some stuff up. I'm not sure if we're gonna have enough time to cover that on Tuesday. So like as it stands right now, our Final is a week from today. I don't have any issue moving that to the following Tuesday, if you guys want it. I'm okay with either day. If we do move it, then I'll need to come up with some material to talk about on following Thursday. I don't see why I can't figure out brushless machines, brushless machines. That's not gonna impact really how they operate so much as it's just a different way of exciting the armature ones. Matthew, you had a question?
So are we having a review there and then lecture?
So it was my intent to go lecture and then test. We could, so if we push the test back from next Thursday to the following Tuesday, the last day of the quarter, that would potentially give us a day to actually have review as well. It is entirely up to you guys as to which you want.
No. Yeah.
Okay, so keep it on next Thursday. All right,